Welcome all. In this lab we are going to learn how to generate different kind of signals uh, that we need in signal processing. So in theory classes you people have studied about different kind of signal and its respective function, or you may call as their respective equations. That theory we are going to implement in this lab using Python programming. So along with that we are going to discuss about some basics operations like shifting, scaling and reversal on different kind of signal using Python programming. So before going into the programming section, let me list out what are going to be discussed in this lab. Okay, so for that I am listing out the things here that we are going to actually discuss in this lab. So first we are going to discuss about different kind of signal generation used in signal processing. So which kind of signal we are actually going to discuss is, let me list out here, that first is cosine signal, then sine signal, then sinc function, then signum function, or you may call sing. Signum is written like SIGN, signum function, then the basic signals like unit impulse, okay. Then unit step, then various signal like rectangular pulse, then triangular signal, this much. Okay, these things we are going to discuss in both uh, discrete and continuous domain. Okay, except impulse unit impulse signal. Okay, all are we are going to discuss both in discrete and continuous domain. So then second thing is some basic operation on various kind of signals, like shifting, then scaling, then reversal of signal. This thing also we are going to discuss in two domain. One is continuous domain and second one is in discrete domain. So that you people get a clear idea about how actually the shifting and all the things happen, which is shifting is very much essential in the convolution part, and it will be very much helpful for you people. If time permits, we are we are going to discuss about the sampling theorem also. Let me write it here. If time permits, we can discuss, otherwise we will take this sampling theorem on next lab. Okay, sampling theorem. So if time permit, we are going to discuss how to implement this sampling theorem in using Python, and how actually effect we are going to study about aliasing effect, what is down sampling, what is up sampling, how we are going to implement that things into Python code. All the things will be discussed there. Okay, so let's start with our first thing, that is different kind of signal generation. In this part there are various kind of signals are there, so we are going to learn one by one. So let's start with our first signal generation, that is cosine signal. Before going into that, let me rename this file first. Okay, it is about lab 4 signal generation. Rename it first. Okay, then let me add another cell. In first cell, I am going to call all the required libraries for our programming. So I am importing import matplot leave dot pyplot as plt. I think if people know how to use matplot library in Python. In lab number 3 we have discussed in data visualization part, you discuss these things, how to actually plot the things in Python using matplot library. So we are going to use those things in this lab. Now the most important library, that is my numpy library, I am going to import that here also. Import numpy as np. Okay, so these two library is enough for today in this class. So this much, then go to the next cell. So here I am going to write the code for the generation of cosine weight. So generation of cosine signal. Okay, so for that, let me you people know in a signal there must be some amplitude, frequencies, and some time period must be there. So I am declaring that. So for my amplitude I am taking A. In every program, the A, capital A, signifies the amplitude of the signal. So I am not going to repeat these things in every uh, signal. So keep it in mind that capital A means my amplitude. So I am taking my amplitude as 3, then frequency is equal to, let it to be, I am taking as 10 hertz. Okay, so as it is a, I am doing now with only for continuous. Let me add a heading here. Sorry, to be not added. So let me add insert. Okay, so here just undo this. So I am adding a heading here. That I am doing for continuous time signal. Or maybe CT signal, you mean continuous time signal. Okay, so this is for continuous time signal, and later on we are going to study about the discrete time signal. So make it as small term heading. Okay, so this is for CT signal. So CT means continuous time signal. Okay, don't think about other things. So let me give the time. As it is a continuous time signal, it must vary with time. So I am going to define a variable for time. Let it to be small t is equal to, I am generating a array here, that is using numpy library np dot line space or linear space lin space. This also we discussed in our previous classes, so you people know these things. Okay, so I'm starting from 0, my ending point is 1, then I'm going to take 1000 of sample. Okay, so the time is generated here. So x is equal to a into np dot cos to into np dot pi, because all these things, the cos function, the pi, these are all there in the numpy array. So as I only called that numpy library for using each function of that numpy library I have to use like this: np.py. I am using numpy library to extracting the value of pi from there. Okay, so that's why I am writing here np.py. So then into frequency FRE. If people know, I think, what is the equation of the cosine wave, so I am writing that thing. I am not explaining that thing again. So into my t. Okay, so my signal function is created. Now I am going to plot it. So plot dot plt dot, let me set a figure size first. Figure then fig size is equal to, I'm taking 10 size, okay, 10 length, 10 width. So then plt dot plot, let me plot it. In x-axis t, in y-axis I am going to plot x, then in, let it to be, let me set a color for this, so let it to be red. Okay, so next plot dot title, let me give a title here, plot dot title. Okay, so cosine signal with frequency is equal to 10. Okay, this is my title. Then let me put the x level here and y level. X level is my time. Okay, in second, then okay, let me give here the size also to be better, fix font size. Okay, is equal to, let it to be 20. Okay, for this font size, let it be set it to be 15. Okay, so for y level, let it to be, let me define it okay, is amplitude, right? Then here also font size, let it to be, make it same, is equal to 15. Okay, I need grid here, so let me call the grid also. Let me check the program here before running it. Okay, so I'm running now. Shift enter. See, a cosine signal of frequency 10 is generated here. Okay, So I can change the frequency to 5. We give a good picture, so let me modify it. Okay, 5. See, still working. Okay, like this we can change the frequency, the amplitude, and other things. The time space, we can increase the time space here, the time limit. We can change other things here to generate the signal. So in this way, this is for the cosine wave. Okay, if we want to plot the sine wave, the only thing which we are going to change here is the, I'm copying it from here to save some time. So you people don't copy these things, and please write it again for your practice. Okay, so I'm copy and paste here. So to see all the things I am keeping the same, and what we have to only change is the sine is going to change, the cos is going to change at sine. Okay, let me write it for the sine. Okay, the sine signal. Okay, here. Okay, that's all changes has been done here. So let me run it. See, a sine signal of frequency 5 is being plotted. Okay, so next one is our sinc function. Okay, let me write the code for that, how to plot the sinc function. This sinc function, you will learn these things in theory classes in that Fourier transform chapter. So you people going to learn this that function, how actually the sinc function works in Fourier transform. So I am not going into that things. I am try to implement that theory into Python programming. So let's start. So for that, okay, I am going to plot the sinc function here. Okay, sinc, we call it signal or function. Okay, so for that, this also a continuous signal. So let me define a time for that. Okay, so for that t is equal to np dot linear space I'm declaring the time as from -10 to 10 with 2000. Okay, then S is equal to only sinc, no sinc, I have to call the numpy library np dot sinc. Okay, like sine and cosine, sinc also a function, so I'm calling that from the numpy library. So I'm going to give the variable as t here. Okay, so after that, let me plot the signal. plt dot plot. Let me set a figure size. Fixed size equal to okay. So then let me plot it. Plot in x-axis t, then in y-axis my s. Let the color to be red. Okay, you may put as a green also, no problem. So next let me put the title here. Plot, sorry, plt dot title is sync function, plot of sync function, that is to be plot of sync function, to be font size of 20. Okay, like that the x level and y level. I am not doing that y level because always it is we amplitude as we are plotting the signal, so I am only writing the x level here. So you people write it all x level and y level. My x level is here also type. Okay, I am only writing the x level. Okay, then the grid, plot dot grid. Okay, so let me check the program. Let me run it. See, this is a sync function. Okay, down. Okay, this is better. Okay, so I think this is clear. There is no anything nothing to tell about this code because we are only using that sync function and we are just plotting the things. Okay, so let's go for next one, that is mine some basic signal, like let's first plot the rectangular plot. Okay, so for that let's write the code. Okay, so for rectangular plot, rectangular generation of the rectangular signal here. Okay, okay, so similar to others, let me define the time limit. We dot length space and -2 to to be 2 with 1000 of sample. Okay, then we have to define the rectangular function. I think you people know what is the equation for a rectangular signal, so I am going to implement that things. So see it here. So rectangular, so if it is R is equal to one into the absolute value of t that we taken less than is equal to 0.5. Okay, so this is the equation to plot a rectangular signal. So here, then similar to others, let me copy it from here, that I have to only make few changes here, so I am just copying it from here and make change to save some time. Okay, plot of a rectangular signal. You write, I have to write like this. I think it is okay, so let me run it. See, a rectangular pulse of width of 1 is generated here. So based on our function we that we define here, it is generating a rectangular signal here. Let me write the x y level also. Okay, with the font size of 15. Okay, so okay, in this way we are going to generate the rectangular signal. So one thing I want to mention here, that if people know how to save this file and other things, so I am not repeating that things again here. In data visualization lab we already discuss about the things, how to save the image or plot in your desktop or PC with in different formats like JPEG, then PNG, TIFF, any format we can save these plots. So I am not again going into that. If you people want, you people add the command here and you can save those these plot into your PCs laptop. Okay, so next go to the next signal part. Okay, now let's see for the triangular signal. Okay, so make it triangular. Okay, so let me define the time this here time t is equal to length space and same minus 2 to 2,000 of samples. Okay, then I have to I have to write the function for the triangular signal. So for that, let me define the variable as capital T is equal to start bracket here 1 minus absolute T then into absolute T less than 1. Okay, I think this is right. Yes, no issue with this. Okay, so the function has been declared here. What we have to do, only we have to plot the thing. So as we have to plot the same thing, I am not writing this, so I'm just copying from here and pasting it here to save some time. Okay, so but I have to plot it, the triangular function T, it to be green, to be rectangular, it is to be triangular. Okay, and all the things remain unchanged. So okay, so I'm going to run it. Some error has occurred here. Let me figure it out. Lens space. Okay, I didn't specify the NP here. That's why it is showing some. Sorry. NP dot lens space must be there. Okay. See, triangular signal of width of 2 has been generated here. Okay. With, like this we can generate the basic signal. Okay, so let's see the for the other signal. Now let's plot the Signum function. So for that, let me write the code. Okay. So same, let me declare a variable T to 2,000 samples. Okay, so let me declare the function now. So for that, let me capitalize is equal to function is 1 into t greater than is equal to 0 is equal to 0, the value will be 1, and minus 1 into t less than 0. I think this is correct. Okay, this is the function for the Signum function. Okay, this is the equation actually, not function. This is the equation for the Signum function. So now it is ready, so let me do the plot part. Like other plotting, let me take it from here. If people please don't copy paste, please write it again. It will increase your practice so that you can perform well in your exams and all. Okay, so I am copying from here to save some time, nothing else. Okay, so you people please write it, don't copy paste. Okay, plot of Signum function. Actually it is a function. Okay, or sometimes it calls signal also. So, no, nothing to worry. So signal, let it to be. Okay, other things. Okay, I have to change the name here to put the capital S here. Okay, so let's run it. See, this is the Signum function. Okay, let's see some modification in this program. You people might have some doubts, so let me do some modification in that. So if I increase the time limit, see whether it will going to affect. Let it to be like this. Okay, see it is changing here also. So let me increase the sample size here. Okay, in this way you can change the things here. Okay, you can add the another suppose if you want to add another another waveform of a triangular type, so you can add by modifying here. Okay, by modifying the time limit, and again we have to add a signal. With this means we have to modify some in this function. We have to make some modification in this function such that it will again define the same things, and it will generate the another wave of triangular signal. Okay, there are other libraries like scikit and all, where we can generate a continuous rectangular wave, continuous triangular wave. Okay, these things little bit difficult at this moment. That's why I am not going into that things, and I am strict to these things because it is a little bit easier for us to understand the things in a clear understand the things clearly. So I am not going to that library and explaining that things. So if anyone wants, they can obviously do with scikit and all and other libraries that are available in Python. So in the, if time permits, I can show you how to install that scikit library in Python. So let's first finish all the things that we have taken to discuss in this class. So our next signal is Signum is over, so let's plot the unit step. Okay, so for that, let me, so I'm doing here for unit step. I'm not writing the comment again here. Okay, so I'm directly doing declaring a variable here, np dot then space. The people know a unit step signal is that which is a continuous time signal from 0 to infinite. So as we cannot go to infinite in Python programming, so I am giving some limit here. So let me declare it from 0. If you put some minus value also, it will not, I will show you that. Okay, so let me give it from 0 to 10 with 1000 samples. Okay, I am declaring unit step, so let it to be u is equal to, like that means what I have to do, 1 for all values which is 1 for all values for time t greater than is equal to 0. In 0 also we have our signal values as 1. Okay, so let's see with this, otherwise we can modify something. Okay, so my function is ready to use now. So let me, for plotting part, let me copy it state. So I have to plot with versus u here, let it to be red. You can change the type of line also. Here you are seeing a line, you can make it that shaded line. Okay, that all things has been taught to you in that data visualization part. So let me change the triangular to unit step. Okay, unit step signal. Okay, other things remains unchanged. So let's see. Okay, if I put equals to, it will not taken. Okay, I got it. So don't put equals to here. Okay, it will taking the values as 0, because equals to, it will again multiply it with that 1, so it will make it 0. Let's see. Okay, let's see if I put if I want to see from minus values whether it is there or not. Let's check it. Minus 2 to 10. Let's check it whether it is there or not. See, in negative values there is no values of the unit step signal, as we studied in our theory part, that unit step signal is from 0 to infinite. Okay, in later part we can discuss about how to flip the unit step. Okay, in that thing, in that reversal, time reversal, we are going to discuss this how to plot u of minus t and other things. Okay, so this is the all about how to plot the unit step. Now let's see the signal that is most commonly used signal, that is unit impulse signal. Okay, so for that, as we know, for impulse also, the impulse signal has only a amplitude of 1 at t is equal to 0. So for that, let me declaring a time variable here, t np dot in space to be 0 to 2, sorry, 0 to 2 1000 number of samples. Okay, then I am going to pulse I am going to generate an array using numpy of zeros. Okay, to make the length same. See, here I am putting the length as 1000, here must be 1000. If you are not if the length is not matching, it will show an error. I will show that. Okay, so let the impulse at 0 at 0 location is equal to 1 and all are zeros. Okay, so let me plot it now. So let me write it, plot plt dot plot. If I write, okay, let it to be, I am not increasing the figure size now. Okay, I am directly plotting, so you people know. So let me, so t versus my impulse. Okay, with let's give a color to it, let it to be red only. Okay, then x level, y level, give it, it's better. I'm not increasing the font size here, let it to be. Dot sorry, x level, y level is amplitude, my x level is time. Okay, time, put the title here, plt dot title as impulse signal. Okay, put the grid for better understanding. Plot grid. Okay, then run it. Let's see. Okay, some error has come here. Impulse at time is equal to 0, it has a amplitude of 1. Okay, so let's see, as I told you earlier, if I change the length of arrays and my time variable different, let's see how the error is going to see. This type of error is going to show to you. See, x and y must be of same dimension, but we have a shape of this much and this much, so for that we have to make the size of both the x and y similar, okay, for plotting purpose. So be careful when you are plotting something, the size must be same. I think it is clear to you. So these are all about the continuous time signal. Now you are going to see how to plot these signals only in discrete time domain. So for that, let me give a heading dt signal. Okay, so it has a heading here. So now we are going to see the dt signal part. Let's see the program for cosine wave generation. So for that, let me comment it first. Cosine wave in dt domain. Okay, now we are going to plot all the signal in discrete time domain. As all you know that for discrete time we have to specify length of the signal. So for that I am specifying L is equal to, let it to be, the length is 50. Okay, in case of continuous time domain we specify there the time limit, and in case of discrete time we are specifying here the length of the signal. So then the discrete domain time, that is nothing but the small n, let me define it, is equal to np dot arrange I think if people know what the np dot arrange function do, we already discussed these things in basics of Python, so I'm not going into that again. I'm proceed with the program here. So let me define a amplitude for this. Same, I'm defining is equal to 3. Then the frequency let it to be, okay, for discrete time domain what will happen if I take the frequency more like 10, 20, it will the signal will not clear that much, so I am taking very less amount, let it to be 0.1. okay, I'll show you if I take larger number how it will actually look like, so don't worry. So let me take the frequency at 0.1 and proceed. So cosine, so capital C is equal to, let me define the function for that, into np dot cos then to pi 2 into pi. Pi means I have to use np dot pi because I am not in these things. Okay, np dot pi to pi ft. So f here is frequency, f r e q, into here t is n. Okay, small n. So my function is ready now, so let me plot it. plt dot okay. In mat, this plt means the matplot library. Okay, in that there is a function that is called like plot. In plot, what we are doing there is we are plotting a continuous time signal. Okay, but to plot a discrete time signal we have to use the function stem here, stem. Okay, stem. Then by default the x-axis will be my time, that is small n. So you can specify. If I not specify that thing, it will also good. Okay, means the signal will run, there will no error. So let me try that. Let me give only the function c. I'll tell with time also. So let's see whether it is actually running or not first. Then other things like plt dot title plot of cosine dt signal let's make a font size of 20. Then plt dot next is my x level. Let me level is time. Okay, make it the font size is equal to 15. plt dot y level is my amplitude. Font size of 15. Okay, let me run it. See, the cosine signal in discrete domain has been plotted here. So let me change the frequency that I have already told you that if I increase the frequency, let it to be 1. See, people not going to get a clear plot. So be careful and plot with small frequency such that you will get a clear plot. So let me make it less 0.01. It will make good plot here. Okay, it is very less here, so 0.01 is good. If I change the length, it will be Like in this way we are going to generate a cosine wave in discrete domain. Okay, if you want to increase the figure size, let me do here. If I put, see here I am not mentioning the time in x-axis. Let's give it now n comma c, whether it will running or not. See here also there is no such error. Okay, we can put grid here, plt dot grid. Okay, let's see, it's coming. Okay, if we want to increase the figure size, let's try. I don't think so it will increase because of the stem function. Let's try it. Figure fixed size is equal to be 5, 10, sorry 10.5. Let's see. Yes, it's working. Okay, like this we can plot the sine wave also. So for that, let me put the code from here. If you will just write the code again. Okay, I'm just copying the code here from here. Okay, I'm going to plot the sine wave, so change it to sine signal. What I have to do is I have to make here site. Okay, everything is fine. Let's run it. So the error has come. Let's see what's the error is. NumPy has a attribute sine. Okay, I have mistake. Second. Okay, see, this is a sine wave. Okay, in this way we can plot a discrete domain sine wave and cosine wave. Then let's see for the Signum function. Okay, sorry, now we are going to see actually the sinc function. I just confused with Signum and sinc. So let's start to plot, to generate the sinc function in discrete time domain. For that, okay, so we are going to do for the signal. Okay, so let's write that n is equal to you can specify the length also. Suppose the length is equal to, no, here what we have to do, see, the sinc function is a two-sided signal. Okay, for that, so due to that, let me define a variable small n with linear space of, if I specify the length here, it will not generate the negative side part, so that's why I am using the here the linear space attribute of NumPy array in space to generate a two-sided signal. Okay, so we'll start from -2 to do with, let's do it 100 sample. Okay, we make this 10 to, because in our previous example we have take 10, so let's try to take the 10 here. Okay, then sync, let's define x is equal to np dot sync, np dot sync, then n. Okay, then the plotting part. So for that, let me copy it from here. Plot of a sync function, sync signal, this much, and okay, I can add a figure plot size here. Okay, let me plot it plt dot, as I am doing the discrete in discrete time domain, so I am going to use stem here, and I have to plot x. So x, let me define the figure size, plot dot figure fixed size is equal to 10,5. Okay, now let's plot it. See, this is the plot of the sync function in discrete time domain. Okay, so see, the only what I change here is I take less number of samples. Okay, see, in the continuous time domain, what I did here is I have taken 2000 samples. See, if I take here 2000 sample, how the plot it looks like. That's the only reason I change the sample to 100. Let's see, to verify that, let's see that. It will take more time than the first one due to the number of sample. Okay, see, that's the reason I have taken a less number of sample here. Okay, sorry. Okay, let's run it. I think if people got this, so now let's do this for sync is over, so we can now proceed to the rectangular part. Okay, the rectangular triangular wave I am not doing actually. If people try it and try to do that, if you will not getting, then I will help you. So that part I am leaving to you, and I am directly going to that unit step function. Okay, that's an important signal in discrete time domain. So let's try to plot that to get a clear idea. Before going into that unit step, let's see for an exponential signal, because in continuous time domain we didn't see the exponential. I didn't mention that things. You can do the exponential plot also in continuous time domain, but you try by your own that exponential part. I am not going to do that. If you people find any difficulty, then I will help you. So now let's see how to plot a discrete exponential curve or signal in Python. So for that let me define L is equal to, I am taking same 50. Okay, let me give a heading here. Exponential signal. Okay. DT signal. So now let's define the time frame. N is equal to NP dot a range L. So then let me define the function exponential capital E is equal to sorry, NP dot exp, the attribute of the numpy array, with minus 0.5. I am taking 0.5 into n. I'm going to define it from 0, so means 0 to that limit 50. Okay, I'm not going to plot that negative part, means it's a one-sided signal. Actually you can plot by a two-sided signal, okay, but I am doing only a one-sided signal here. For that I am giving here that n should be greater than equals to 0. Okay, now the function is over. Now let's plot this. So for plotting I am just copying the thing from here. So I'm going to now plot the E or n comma E, then let's say exponential DT signal. Exponential, let it to be exponential DT signal, then the time and amplitude. So let's run it. I think it's clear. See, this is the plot of a exponential discrete time signal. You can change So let me change it to 0.2. Okay, if I make the change here, like if it is less than, let's see what actually the output is. It will not come. Why? Because the time limit here I have given is 50. If I take it to minus 50, see, it will come. Okay, some error has is there, so let me zero size arrays reduction operation. Okay, it will not happen. Okay, so we can plot it. Is it negative? It is not coming. Or we can flip it in that shifting in that reversal. I will tell you how to shift this signal. Okay, so in that you people get a clear idea how to make a positive sided signal to a that negative sided signal, means that x positive to x negative. So in that you will get a clear idea. So run it for this. Okay, now let's see for unit step signal. Okay, so for unit step I am directly writing the code here. So let me declare a variable, that is the for length L is equal to, I am taking 50 samples, so generate a array p dot arrange. So okay, so now I have to mention the signal u is equal to 1 into for n greater than 0, now I have to plot the signal. Okay, so for that let me copy it from here. So I'm going to plot for u. So let me put u here and it's a unit step. So now let's run it and see. Okay, in this way we can generate a unit step signal. Okay, the sample at 0, let me define it is equal to 0, whether it is coming or not. Let's verify. Yeah, see, in 0th sample also it coming. Actually the unit step is from 0 to infinite, as infinite is not possible here. I am showing to up to some length. So and from 0 it will go to the up to 50, because I mentioned the length of the signal is 50 in my program. I think you people got it. Okay, so this is about the signal generation. Rest of the thing, that triangular wave, then rectangular signal, okay, this stuff you can try to do it in discrete domain, because I have already told you how to generate in continuous time domain. So I am not going into that thing, okay, to save some time, because I have to cover other things in this lab, like we have to do now that basic operation on signals. Then if time is there, then we are going to discuss about the sampling theorem, and we are going to learn about that how to install some library that we are going to use in our next lab. So for that reason I am not doing that. So if people just try to do it, if not able to, if you are not able to do that, I will explain that thing also, so don't worry about that. So try it first. Now let's start the basic operation on signal. Basic operation. Basic operation on signals. Okay, operations like, let me make it as heading first. Operation like the shifting, scaling, reversal, these things we are going to discuss here. Okay, so first is shifting. First we are going to see the shifting operation in a continuous time signal. Okay, shifting on a continuous time signal. So I am taking a exponential signal here. Okay, okay, let me define a function here. I think you people know how to define a function in Python. xt, I'm taking t here, then sorry, I have to put a colon here. Then return a exponential function to here, np dot exp to be minus 0.2, the same signal that I have plotted in the discrete domain. I am going to plot it for your getting a clear picture. Okay, into t, for t greater than is equal to 0. Okay, so I think this is over. Now let's give the time. Sorry, let's generate the time frame. T is equal to np dot linspace. Okay, I need it from -10 to 10 with suppose 1000 of sample. Okay, so now let's plot it. The signal is generated now. Now let's plot the signal first, then we are going to see how actually the shifting is done. So let me first plot the original signal. Okay, so for that let me plot. Okay, I can take it from here, so to save some time. Okay, here the plot is gonna because it is a continuous time signal, so t versus I have to plot the function, sorry, xt. Yes, plot of a exponential, or you can we don't need this, I put the comma. Don't do this actually. No, you can add it this after the shifting and all. Okay, so first plot it, the original signal. Okay, let me define, no, otherwise it will blue in color, nothing to worry. See, this is the my original signal. Now let's shift the signal and plot it in the same graph. So for that let me do like this, that is plt dot plot t comma my x. Suppose I want to do time advancing. Okay, so t plus 2. Okay, and the color, let's change the color as we are plotting the same graph here, so let it put in red. Okay, now let's run it. See, this is time advancing. If I do, I think you people get a clear about. See, this is my original signal, okay, and this is my time shifted signal with a 2 unit. Here the scale is different, we can change the scale also. So now this is for time advancing. If I do for time delaying, let's here I make the change to minus. See, this is time delay. Okay, and suppose what I am going to do is, let me add a DC component to the signal. So I am adding a DC component here to the signal. Let it to be 5 plus this is my xt, 5 plus exponential e to the power minus 0.2 t for t greater than is equal to 0. So let's see how actually it looks like. So this is for time delaying. So let's see for time delaying. See, in the previous plot you can notice that there it is 0, but here it is from 5. Let me clear it by setting the limit, that is plt dot x limit is from 0 to, it is coming from 6 log 10 with a incremental size of 1. Okay, some error is there, not x limit, it's y limit. Okay, I'm changing the y limit here, so that's why it is. I think now it is clear. See, 0 to 4, then it is 5, because I am adding a DC component to the signal, so that's why the signal is shifted to the upper means up to 5, and then it's plotted. So in this way we can see, you can plot the time shifted signal in continuous time domain, and we can do it for the discrete time domain also. So I think people clear about this thing. So now let's, one thing we can do, okay, let me that explain in another, because here the time, let me write it here, time advancing and time delay and advancing. Okay, both are done here. If people do the time advancing in a one cell and time delaying in another cell, such that you will get a clear idea how actually it is the time delaying and time shifting, time advancing is actually done there. So now let's do for time reversal. So for that, let me the code, because the same thing in continuous time domain only I am going to do the time reversal. So okay, I didn't copy this. The shifting is over for continuous time domain. Now we are going for time reversal, then the scaling is there, so we can do that. So let it to be reversal. Okay, time reversal, because we have to cover a lot of things, so time is not there. So let me little bit fast now. For time reversal, let's do like this. Okay, I have to put minus t here and plot it. Sorry, we don't need this one now. Okay, it's I think clear also. Okay, let me do it without 5, it will be clear. Due to this DC component, it is little bit difficult to interpret actually. The limit discrete also we don't need now, so just remove that. Now it is clear. The blue one is my original one, okay, and the red one is my time reversal one. Okay, you can add the legend in that. I'm not going into that. In data visualization part I already told about how to add a legend and all, so try to add those things into that. And now let's see for the time scaling. Okay, so shifting is over. Now scaling of city signal. Okay, for that we need the same program, not big changes there, so let me copy it. We can save some time and we will discuss more thing in that time. So let me hit and paste it. Okay, the same expression I am going to take it, that is that same exponential signal. What I can do it here is that I'm going to make time scaling. Suppose I am going to do 2 into, in time scaling also there are two. One is that one is compression and one is dilation, or you may call as it's as a expansion. Okay, if the factor is 2 here, it means it is going to be acts as a compression factor. So now let's see. I think you people know about in from theory classes. So now let's run it and do. This is actually the compression. You can check it from here that the signal, the original signal is this one and the compressed signal is this one. If okay, so this is for compression, so let me define it for the compression here. Signal compression. Okay, so let me do it for signal expansion or dilation in the next cell for your for the clarity. So signal compression is over. Now signal expansion. Okay, for that the factor has to be changed, so I am expanding the signal 0. Let it to be 25, means t by 4 actually. So let's do it and plot it. See, the signal is gets dilated here. Okay, my original signal is this one and the expanded signal is this one. So in this way you can do the scaling in different kind of signal. Here I did this with a exponential signal in continuous time domain. You can do it with other signal also. Okay, so the shifting and scaling is over now. I also see for I also give you about the reversal here. Okay, time advancing, then time delaying, then we see about time reversal. Okay, then we see about the time scaling in which we have two things, that time compression, signal compression, and one is signal expansion or dilation. You can call it as dilation also. So I think it is clear to you. So this is all about that continuous time signal. Okay, now let's do it with a discrete time signal. So for that I'm going to take a same thing I am going to do. So let me copy it from here. Okay, so let me do it for a dt signal. Sorry. Okay, so as we are going to do in the continuous time domain, sorry, in discrete time domain, we have to mention the length of the signal. So for that, let me do that. The length is 50 and I create a variable that is small n with length L. So now let's define a function x of n, then I'm going to plot this exponential graph in discrete domain. Okay, so I just defined that graph here. Now let's plot it. So for plotting I just use these things. So I'm just, to save some time, I just quickly writing those things, copy paste, and okay, let's do this now. Okay, first plot the xn. Okay, so it is exponential discrete time signal. Okay, everything is fine. Now let's run. See, this is my original signal x of n. Now I am going to delay the signal, okay, with 2 units, and I am plotting that signal in red color. So now let's run it and see how it is actually. See, this is my delayed signal, time delayed signal with 2 unit. Okay, so now I can so in this way we can delay a signal okay. So now let's see for time advancing. If I put here +2, now let's see whether it is coming or not. I think so, it will show some error because of the time. Let's check it. Okay, it is actually not coming due to the time axis problem. Let me figure it out first. See, I just figure it out actually what's the problem arising there, why we are not getting that time advanced signal. So what I did here is the time axis I have just changed. Okay, we without length also we can use it. For putting that theory into my program, I just use that length function. Now what I am going to do is I am generating a array of -10 to 10 with 20 samples for easy understanding, for get good visualization. I am taking only 20 number of samples there, and what I did was the same function I have taken, then I am going to advancing it with 2 units. Now let's run it. And see, I just run it, you can check it, the signal has been advanced to 2 unit. If I delayed it by 2 unit, it will also going to have same thing. See, delay. Okay, I think if you will get it, we can do like this, the reverse operation. Okay, so 2 minus n, let's check it whether it is coming or not. Yes, it is. Okay, so you can check it from here. So yes, it is. Okay, so now the time advancing and time shifting in, sorry, time delaying in discrete domain is clear to you, I think. So now let's see for time scaling, because we have very less time. The decimation and the signal, actually the scaling of DT signal is little bit different, because here what we have to do is if we are decimate the signal, it will reduce to half of the sample, so it is little bit difficult. So what I did was I write the program here, and I am going to tell you what I did. Actually, I choose the length of the signal is 50, then I take another variable x. I'm going to tell you why actually I am take this x in the plotting in next stage. So these things you know. Then I take another range of array, another array of y, that is of I take the value from x here. This x and y is only for the plotting purpose. As I already told you, for putting the dimension same, for plotting we need the dimension same. So for that reason I am using the these two variables. I am going to decimate these things by 2 unit, means by a factor of 2. So what I am going to do, I am using the slicing property of the array in Python, and I am just reducing the size of the array of the signal by 2, factor of 2 here, and I am just plotting the things here. So if I run, you can see here that this is my original signal, blue color, and my red is the decimated value. Like that I can expand the signal also. So for that I am going to use the same program. Okay, so let me little bit fast, I have very less time, and I am going to use same signal. But what I have to do is, I have to, as I am going to expand, so my signal expansion, okay, these are all in scaling. So what I am going to do, I have to make this x as 100, because I am going to again the same thing, the slicing with because the length is 50 here, and I am going to expand it by a factor of 2. That's why I am taking that this variable x as 100 here. Then all the things right, yes. Okay, for dilation, the changes that I have made here is the major changes is here. I just add another variable s with a double to length of the original signal, and what I did was I just reverse it, because in expansion or dilation what is going to do is the signal is going to be means dilated, means it will going to, the length is going to be doubled, but in compression the length is going to be reduced there. So what I did here, I used the same slicing concept but in a reverse manner. I just assigned this to the value of e to this one, okay, s array that I have created with double the length of the original signal. So this is for the clear visualization. I just reduce the length, and these things I have done. Then I just plot it with the stem attribute of MATLAB plot, and let's run it and to see how it is actually working. See, this is my original signal, blue color one, and my dilated or expanded signal is the red one, and you can see it from here that my signal is get dilated. Okay, so in I just, what I did is means I extend the signal by a factor of 2. So in each after one sample there is a addition of 0, then here it is 0, okay, then this signal is coming here to this position, like that it will done. So I think this is done with we're done with scaling. Now let's do it with reversing. For reversal there we don't need much more, so let me copy it from here. So we are going to do the reversal now. Reversal of the signal. So for that let's run it. The only changes I made it here is I just make it x of minus n. Okay, let's run it whether it is showing the result or not. You can check it from here that my signal is get reversed here. Okay, this is my original signal, this is my reversal signal. In this way we are going to do this basic operation on both continuous time and discrete time signal. I think it is clear to all of you, and you will do other with this type of operation with other signal also. So okay, due to lack of time we are not discussing that sampling theorem, and we will discuss that things in next class.